Well, this is section 5.1. We will be looking at a proposed improvement to that method of exhaustion that the Greeks and other ancient peoples used, which we called the rectangular rule. And we're going to move on to something called a trapezoidal rule. And I think it doesn't take you too long before you realize that you're not taking very good advantage of your geometry. If that now is a curve and we're trying to take the integral of that curve, for us to make a series of rectangles under the blue line and add up the area of the rectangles, trying to imagine that to be our area, we are institutionalizing a lot of loss in that. Why not run a sloped line between the 2 points? Why not introduce the idea of approximating a curve with a straight line? We're used to doing that. We've done that with Taylor series. The first order term of a Taylor series is really just a linear approximation. Why not apply that same idea here? Well, we're going to look at that geometrically instead of through the Taylor series, at least at this point. We're going to come back to Taylor again. But for right now, we could visualize the area under the blue curve. So here's our blue curve. We could visualize the area under that blue curve as being represented by a trapezoid. The trapezoid would have the leftmost height as being the functional value at the starting point, which we're calling A. And the height at the right point, B, would be the functional value evaluated at B. Then we would just simply draw a straight line between the two and complete the trapezoid by dropping vertical bars down to the axis. And the area that I'm highlighting with my mouse represents the trapezoid that will approximate the area under the blue curve. It's very easy to come up with a computational formula for that, where if you look at the formula for the area of a trapezoid, it's just 1/2 the sum of the two heights times the base, and the base is b minus a, and the sum of the two heights is f of a plus f of b. So there's our nice trapezoidal area formula, which also is called the midpoint rule. And I don't think it's too hard to see why. If you apply that 1/2 to the function values, you're really taking the average height or the average height across the trapezoid. And so that's why it's often called the midpoint rule. But it's still a trapezoid nevertheless, and we're still using the area under that curve. Okay, so how well will that work? Well, here's another picture of the same trapezoidal rule, except applied for a function of 1 plus x squared. And we've broken this into 3 trapezoids rather than 1. So we have trapezoid 1 on the left, 2 in the middle, and the third one on the right. If you imagine those little trapezoids there producing an area that's approximating the curve, that clearly is better than if we had done that with rectangles. Whether you put the height of the rectangle on the left or the right of any one of these intervals, you're going to get a lot of data loss, either overestimating or underestimating. That won't happen if you use the trapezoid. So there's clearly an improvement that we're going to get out of this rule. Okay, let's continue then with the mathematics. Here's our series of points that we'd like to break up the trapezoids into. On the previous example, I'll back up one more time, we had x0, x1, x2, and x3, each corresponding to those vertical bars. So we end up with 3 trapezoids using 4 points. So in our case, in the previous example, n was 4, x0, x1, x2, and x4. The first point we could either call x0 or we could call it a, as we did before. And the last point in our example was x3. That was equal to our ending value, or b. If we use the first notation where we're subscripting the x values, then that helps us create a formula for the sum. So we are taking 1/2 the base times the two heights, or you could say the average of the two heights times the base. If we use a subscripted notation to denote this, then since we're always looking at, say, x1 minus x0 and x2 minus x1, so forth, then we could call that x sub k plus 1 minus x sub k and allow the k index to run up from 0 to 1 less than the number of points or 1 less than the last point that we're interested in. And we have ourselves a computational formula for the sum. So it's not complicated. There is just a number of trapezoids that we're adding up. They're all butted up next to each other, so they capture all the area. And we'll call the result S sub t, t standing for trapezoid. And that is our trapezoid rule. Well, very much like the rectangular rule, we can get some mileage out of requiring that the spacing is always even. So the distance between adjacent points, x sub k plus 1 and x sub k, is always a fixed number. And as usual, we'll call it h. So if you have an h in here, you can factor that out of the sum. You might as well factor the 1/2 out of the sum as well. So your same S sub t formula will be 1/2 h times the sum from 0 to n minus 1 of these points here, of each of the ends of the trapezoids. It's mathematically the same. It's not efficient though. If you wrote a computer program that did exactly that, you would get the right answer, but you would have wasted computation. Why is that? Well, the left value, let's go back a slide again. The left value of, say, trapezoid 1 is the left value of trapezoid 2 rather is the same as the right point of trapezoid 1, and the left point of trapezoid 3 is the same as the right side of trapezoid 2. So we are re-evaluating these functions redundantly as we're moving across the trapezoid. You can see that on the formula perhaps even better, because as I'm taking f of x sub k plus f of x sub k plus 1, it's pretty apparent that as k indexes upward, that the rightmost value of any one iteration becomes the left value of the next one. So we should be able to do better than that. We shouldn't have to add up those numbers all the time, and we will do that in a moment. But first of all, let's go back to our previous example that we had before, where we looked at the square root of x and asked ourselves if we couldn't do reasonably better using the trapezoid rule than we did with the rectangle rule. If we apply that rule and compute all these areas across the 100 trapezoids that we have that are spaced exactly like we did in the previous session with rectangles, we find that we get a much better estimate. We have 0.666463, and we know the answer is 2/3, and that's looking a lot closer to the real answer than we had before. It's hardly any more work. We've made a few more functional calls because of the wasted overlap, but they're the same number of intervals. So here we have the result, and the difference between the two is now good to give us perhaps almost 4 digits of accuracy. Not quite, but close to 4 digits. We are getting an improvement of 20-fold without increasing the number of calculations by at most about 2. We are perhaps doubling the calculations because of this overlap between the left and the right side of the interval. But for a factor of 2 increase of calculations, we're getting a 20-fold improvement in the accuracy. So that's really a good deal. Now, if we continue to move on, we can, we've already talked about the waste of calculations, and we should be able to get rid of that waste by just doing a little bit of algebra. So here's the formula that we had previously, and we're going to see if we can't look at the overlapping term by expanding out the calculation the long way. So here we're just sort of looking at what we have. We're taking f of x of 0 plus f of x1. That's the first term. And then we are also taking f of x1 plus f of x2. That's the second term. And we have f of x of 2 plus f of x3. That's our third trapezoid. Why couldn't we just say this middle one was 2 times the functional value? And the next one is going to be, we'll have 2 x2s, we're going to have 2 x3s, and the only functional evaluations we do that aren't duplicated are the leftmost f of x0 and the rightmost f of x1. So let's group them. So here we're grouping the redundant calculations, and mathematically we could get the same effect by just multiplying them by 2. But we could factor out all those 2's in this expression, and if we did that, the inner n-1 terms could be added first and then multiplied by 2. The very leftmost functional value and the very rightmost one have no duplications by the nature of the trapezoidal construction. But everything else in the middle could be done once and then multiplied by 2. If we do a little more algebra, we could pull out the f of x of 0, the f of x of n, and we could multiply 1/2 h times these sums plus the h times the sum of the interior points. This becomes a preferred method of calculation for the trapezoidal rule. In fact, if you wanted to, you could multiply h at the very end and even do one less calculation. Okay, so that will become a theorem that we'll do. And this theorem, so here this theorem 1 that's in your book, is going to allow us not only to document this functional form for the trapezoid rule, but it's also going to give you an error associated with it, which is something that we always need in a numerical analysis class. So if we designate the symbol t as representing the same trapezoidal rule that we saw on the previous page, and if I is going to represent the exact integral, and now we're allowing f to be any arbitrary function, then the difference between the exact integral and this trapezoidal rule is going to be a function of the square of the step size. That means that this algorithm, this trapezoid rule algorithm, is an order of h squared algorithm. How can we then manage the error? So your next question should be, I'm writing a program, I need to choose an h, because I can't really do my integration until I make some sort of decision. Well, you will have to decide how much error you can tolerate. And if you take an error like 10 to the minus 6th or 10 to the minus 7th and say that's good enough, and you set it equal to the formula that we got in the theorem, you can back into the h term as long as you can get some kind of handle on what the second derivative is of the function evaluated at the worst possible point in the interval that you're working in. Okay, so if you can go through and figure out the worst case second derivative, and the derivatives aren't going to be hard to calculate, then running this formula backwards allows you to solve for h. So that then leads us to the end of the trapezoidal rule, and this rule will run circles around our rectangular rule, and it does it with almost the exact same number of calculations. So with that, we will see you next time.